Thanks, everyone. I hope you all had a good break. Getting started with the second half of our sessions today, we'll be having John Wiegley, who's a principal engineer at DFINITY, where he's using Rust, Nix and Haskell. And today he's going to be talking to us about writing debuggable functions. So, John, I'll hand it over to you. Thanks.
Thank you. This is a technique that I think will not be very strange to people, but I used it very recently in a program I was writing, and it occurred to me how often I forget that I can do this. So I thought a simple exposition of the technique might be useful for others to see that maybe you've also probably used it before, but there may be cases where you could use it and haven't yet. So to begin with, the code that I was working on is some trading software. I call it Trade Journal. The idea here being that I collect a list of events, buy and sell events, also withdraw and deposit, with some simple details about how many shares and what price it was at, and maybe there were broker fees. And what I want is the program to calculate all the profit and loss implications of this journal. So the result should look something like this, where the Trade Journal has figured out which transactions open new positions, which close existing positions, what the gain or loss is, and what the tax implications are. At the moment, I'm only handling US tax implications, but one of the laws we have here is called the wash sale rule, where a losing transaction followed by a purchase within 30 days actually moves the loss into the cost basis of the new position. So I want the software to figure out all of that for me. Now, initially, following the rules of the law, they're pretty simply stated. It wasn't a very hard function to write. And I was able to take a data representation of this journal, which is viewed as a series of actions over lots, where the lots give the details you saw about the amount of the shares and what price it was at, and then annotations relating to the position. And what I want to compute over that list of actions to produce a resulting list of actions that have been further annotated. And those further annotations now include the gain and loss, the wash sale implications. But as I was writing the algorithm and then comparing it against what my broker's report was, I started noticing discrepancies. And as I dug deeper into why these discrepancies might be occurring, I started to discover little fringe details of the law and places where it's not entirely clear. And my broker just made a decision out of many possible alternatives. But I had to reflect that in the algorithm if I was going to get the same results as they did. And what I found is that the deeper I dug into this problem, the debugging became harder and harder. Because even though I could put in a lot of print statements, due to laziness, the print statements would come sometimes not in the order I was expecting. And further, I didn't know where along that series of calculations things had gone wrong. So it was about finding the diverging point when the calculation had arrived at a number that it shouldn't have at that time in the calculation. So this was the original function that I wrote, quite simply a stream processing of actions to actions, which was more easily expressed as a step function that I repeatedly called over each of the input actions to arrive at the list of output actions, since it may be a larger list. And this is a state that contains a history of the things I've seen in the past that may relate to the future for each given action. So that also includes any pending wash sales that haven't been applied to the cost basis of a future transaction yet. And what I decided to do here as I was debugging this was, this step function has a certain inherent complexity to it, which is that it's doing two things. First, it's computing a list of output actions for me, but it's also figuring out how the history needs to be changed for future calls to the step function. So the technique really just boils down to calling out those two parts of the computation. And in my code, it looked like this. I switched from step to two functions, describe and apply, where describe takes that same input action that step would have received, and it computes the list of changes that need to happen to the state in order to compute the resulting actions. And since these changes are merely a description over a history and not a modification of the history, I was able to further lock down the types to reflect the meaning of that function by putting that function in reader. And then I iterate over each one of the changes that are produced by describe and call apply on it. And the sum of all the output actions from apply and its final state history ends up being the same as the output from the original step function. I've included to the right here the number of lines of each of these functions. And what's interesting is that one of these two functions ended up being really quite trivial. The apply function fits on half a screen in my Emacs, and it's quite easy for me by eye to see not only what it's doing, but that I have implemented it correctly, since the implementation of it is so straightforward. Whereas describe still contains all the same complexity that was inherent in the step function, but now I've called out what that complexity is. I can see when reading the describe function, what are the changes that it's producing along the way. But there's something else I gained from this, in addition to just readability, is that after I had reified what these changes were, enumerated all the possible things that this function could be saying about what that input action implies, and I give the list here, there's 8 at the moment, in addition to a new event type, which is part of the history. This made it easier for me to write tests, because the tests not only confirm that the input matches the expected output, I could also assert the test over the list of changes that the describe function had produced, so that I would know how it arrived at that input. And this way, when this is an example of that test. The 2 yellow parts are what I had before I made this split. The green part now tells me what I expect to happen, how I expect the function to behave over its test input. And this became extremely useful because as I kept discovering edge cases in that algorithm that my broker was using, as I would make one little change, often maybe 2 or 3 out of the total set of my tests would fail. And not knowing why it failed would lead to a whole new debugging session that would repeat all the work that I had done before. And as you can imagine, I started accumulating these trace statements that I was rather reluctant to delete because I kept relying upon them so much. But when the test fails in this form, I can look at the output, and I wrote a little Emacs helper function to make this easier to do. It just draws my eye to the exact place where the two executions differ between what was expected and what's now happening. And then I see which change event it is that changed because of the change that I made to the describe function. And then that usually is a very clear indication to me of what the implication of that change is and how it might be wrong, or maybe the test now needs to be modified and the change was right. So if I were to describe this pictorially, I would have my original step function here as an arrow that goes from actions to a list of actions produced in the context of some stateful history. And I now have 2 arrows. So I've taken my original problem and I've decomposed it into 2 subproblems. The one with the solid line, the apply, I made it solid because it's really quite trivial. It's not quite a given. I mean, it wasn't automatic, but it was almost so. The problem itself kind of told me how that function should be written. The other arrow, the dashed line, is the arrow that I needed to discover, the arrow I needed to implement to mimic the behavior of my step function. And then the type at the top is the new type that these 2 decomposed problems mediate through. And as I thought about it in this way, I realized that I've seen this pattern several times before in my coding career, even outside of Haskell. So I have some examples here. So one of them is quite familiar to me, having worked on compilers for many years, is that this breaking up of a compiler into first parsing the input text and then processing the AST, which may to some people seem like the way you write compilers, but believe it or not, when I worked at Borland on their C++ compiler, it was the one that was in Borland C++5. That compiler actually did the entire compilation process in line as one function. So the parsing of the input text and the production of the machine code happened at the same time. And this was done to make the compilation process incredibly fast. And it was orders of magnitude at the time faster than GCC. But it also made the code, as you can imagine, incredibly hard to debug. So the traditional approach then to compilation is break it into these 2 parts. Now, in this case, I've made the processing line the dashed line, but that's not always the case. Sometimes evaluation of what you've parsed is easier than what you parse, and other times vice versa. But I think this, for me, was the most classic case of taking the problem and introducing an intermediate representation that makes the 2 parts of the subproblems easier to reason about, but where the composition of them is equivalent to the original thing you're trying to solve. Another example of this is build and fold fusion. So a key example in the Haskell community is the vector library. So Duncan Coutts, in his thesis, writes about how the vector library now is implemented in terms of an intermediate type called a stream. And the algorithms that are written over vectors build up values in terms of these streams, and then the streams are folded down to give the output result. Now, Duncan is able to use GHC rewrite rules and a few other fancy tricks to make it so that the final executable code that does the fused operation doesn't have this stream type in it. But by introducing the stream type, it allowed certain simplifications and the ability to reason over these vector functions and what they would be doing easier than the resulting fused function. So I recommend people to check out his thesis if you're curious about how build fold fusion works. It's really quite well written. Another case is Mapreduce. So we have some computation that we want to perform, but maybe that computation doesn't make its component parts available to or amenable to parallelization. So in this case, we break the problem into two subproblems, one where we map over a series of inputs to produce an intermediate list, and another where we reduce over that list to get the final value. This time, maybe it's not being done for simplicity or performance. Maybe now it's being done to expose the parallelization opportunities. So that just is another example of where we're doing this decomposition, but there are different properties we can get out of it. The premise of my talk is that this is valuable for testing and debugging, which I found it to be, but it can also be used for other things as well. I'm running a little bit ahead of my time here, so I want to take a pause and allow any questions that people might have at this midpoint before we go further. Rebecca, do you know if we have any questions pending?
I'm not seeing any in the chat right now.
Okay, then we may just finish a little bit early, and I can move over to Q&A.
Now we just got a couple of questions. Somebody has asked, does this relate to hylomorphisms?
I forgot to put in that slide, but yeah, it does sort of relate to hylomorphisms, where the bottom arrow would be hylo, the left arrow would be anamorphisms, and the right arrow would be catamorphisms. So yes, they do also fit into this pattern.
And another question is, do we assume that describe is always non-lossy?
Not only is that an assumption, as we go a little bit further, I'm going to show that it becomes a requirement for this pattern. The composition of describe and apply must be equivalent to step for this technique to hold. If your describe is lossy, or if your reader hist change can't represent all of the states that step would need to represent all of its outputs, then it doesn't really fit this pattern. But if you can show that describe composed with apply gives the same answers for each input action that step would have given, then it holds.
All right, and we have one more question. Are reduce always homomorphisms or aggregations?
In this diagram?
Not specified in the question, but I assume so from context. Yes.
Are reduce always homomorphisms? So are you? I'm assuming the question is asking, do we preserve the structure of the intermediate type that map is going to in the output type of compute? And that's not necessarily a requirement. Map could be going to a larger space as long as reduce is taking all the elements of that larger space to the same points in the resulting space that compute would have taken the same input to. So for example, parsing can go to a lot of different ASTs that processing could all take to the same output.
All right, I think that's all of our questions for now.
Okay, so as I was looking at this this pattern and thinking about it, I realized that there's something that was very, very familiar that was tickling in the back of my mind. And I went to Wikipedia to confirm, and sure enough, I have one more. I have one more example before I go one more step, and that's the free monad. So this is another prototypical example here of where we may have a monadic computation that goes from A to MA. And that computation, because of the nature of bind, the structure of what I'm doing, like the actual nature of my computation, doesn't admit of any analysis. It doesn't admit me, well, not stepwise analysis, but it doesn't really let me do other things with that result other than produce the action in MA that my function is there to create. So one common trick is to lift MA up into free of MA in order to sort of turn this monadic action into the AST of a monadic action. And then the free library will give us a method, a trivial method called retract. There's a few others that will do other things depending on what we want from the output, that will reduce our free MA back to MA by simply walking through that monadic AST and applying the binds everywhere that the binds are called out as constructors inside of free. And then my dashed line, usually the dashed line here is actually quite easy if I've already written the arrow A to MA. All I have to do is put my arrow into free of MA, and often I'm done. But maybe I'll initially write the function in terms of A to free of MA, and I have my original MA. But I wanted to note here just that the free monad also fits this pattern of taking a monadic construction and turning into something where now you have an AST of that monad, and you can do things with that AST, like print it out or write alternate evaluators instead of simply the final behavior of MA that you would have had before. An example of this is on Hackage. People are probably familiar with the parsec library for writing combinator parsers in Haskell, which I've done quite a lot of. And sometimes I write a parser that's sufficiently complicated that it runs slowly, and I have trouble figuring out why it's running slowly. And even if I have an intuition that maybe it's running slowly because it's doing too much backtracking, I don't quite always have a good way to find where the backtracking is going too far. And if you've tried debugging parsec parsers, you can add tracing statements a lot in the parsers, but it can be very unclear. It can be unclear for a variety of reasons, but I often will spend a whole day trying to find out where one backtracking is going wrong. So what I did is I took parsec and all of its monadic interface, and I just lifted the whole thing up into the free monad. And this is a library on Hackage also called parsec-free. And by having an AST of my use of parsec, I was able to write an alternate evaluator that in the end calls the parsec evaluator to do the parsing, but on the way of converting that free structure to the final monadic action, prints out information informing me of what's happening. And it'll print it out in such a way that it shows the depth in your terminal, so that each parsing rule is indented a certain number of spaces to the right based on how deep the backtracker is going. And when I'm reading that output, it becomes quite obvious when the backtracker is taking certain deviations very often, and then always finding them fruitless and having to come back before it discovers the rule that would pass. And many times then, simply reordering some top-level parsing statements will give you the performance you were looking for, as long as you know which ones have a tendency to backtrack deeply but fail often. So anyway, that's the free monadic version of this pattern. So if I were to generalize this pattern, it would be this diagram, which is given some problem or function that I'm trying to write, X, that goes from an input domain A to a target domain C, can I decompose this problem into two subproblems, where one of the subproblems may be easy or trivial, or I even already have in hand, but I want to extend through B from A to C such that all I really need to do now is discover R. And now R has the advantage of being written in terms of B rather than being written in terms of A. Or if the dashed line is on the other side of this, is on the left of this diagram, now B is my domain and I don't have to think so much about C, because perhaps B has certain simplicities or attributes that I find easier to work with. The only requirement for this diagram to hold then is the condition in the middle, which is that the composition of F and R are equivalent in behavior to X, so that the same A's will always end up giving you the same C's. I wrote this out as an English description for people that might want to refer to this later, but stating the same thing. If we're faced with a complex problem, as I was in calculating this wash sale rule, can I find two subproblems whose composition is equivalent to the original problem, where one of them is simpler than the other? And now what this gives me is a composition of algorithms that are simpler, clearer, or may offer additional freedoms to my original solution to the problem. In the case of this talk, debuggability. In Wikipedia, this definition of con extensions, which is what this diagram represents, was simple enough that it sort of mystified me for quite a long time. So Wikipedia says that con extensions generalize the notion of extending a function defined on a subset to a function defined on the whole set. So here with this diagram, I have a function from A to B where B is the subset of the problem, maybe not a proper subset. It might be the same as the size of C, but it's some subset of C. And now can I discover an arrow that would extend the arrow F through B to C? If the dashed line is on the left, by the way, we would call it a left con extension. And with the dashed arrow on the right, we call it a right con extension. And it wasn't actually until now, until solving this problem of needing a more debuggable tax calculation function, that I realized this is the pattern I was employing. This is the pattern that intuitively I was reaching for as a way to make my life easier. So then I came back to this definition in the Wikipedia page, and it made a little bit more sense to me. And also this last quote that I'm going to leave you with from MacLean in his book on category theory. He says the notion of con extensions subsumes all the other fundamental concepts of category theory. And then thinking about it in all of these terms, these practical terms, it made me realize that, well, yeah, because what are con extensions doing but taking some idea and allowing you to break it down into its more fundamental parts? I don't yet know, and I need to study as my next part after presenting this. I want to figure out, now knowing that this pattern is a con extension, what do the tools of category theory now give me that will assist me beyond just my base level intuitive understanding that this pattern is a con extension, but now knowing what con extensions imply in the category theoretic context, what does that tell me? What will that add to my toolbox in terms of being able to better leverage the way that I approach these sort of functions? And that is the end of my presentation. So I have time to take more questions.